Hello everyone and welcome back. Now, in the previous few lectures, we talked about continuous time dynamical systems. In this lecture, I want to transition ourselves into discrete time dynamical systems. Now, these dynamical systems are sometimes called difference equation. And the discrete aspect of time in this case represents hopping from one instance to the next, as opposed to the continuous time formulation where you think about flowing from one moment to the next. Now, it turns out that discrete time models can be very appropriate for modeling a number of scenarios, in particular places where we are only observing the data at discrete time intervals. This might be something like day to day, or week to week, month to month, season to season, year to year, anywhere where there's a gap between your sampling of your population or whatever it is that you're trying to model. So in this lecture, what I would like to do is present to you some of the basics, just so that you can get your head around what a discrete dynamical system does and maybe how we can interpret them. Now, just like we did with continuous time dynamical systems, we are going to think of a state space. I'll call this S. And this could be an n-dimensional state space. So elements in here might look like x1 all the way up to xn. Now, the typical state space that we've seen as we've worked through some examples here are places where all of our elements are positive. That typically is the state space that one works with when you have things like populations, right? Having a negative population makes no sense. And we consider difference equations that look like this. So instead of having a time derivative on one side, we have the change in the first variable from one moment to the next is given by some function of all of the variables. Then similarly, the change in the second variable from one time to the next is given by a function of the variables again. And you can repeat this idea all the way down to the last variable here. Now, if you want, you can go back and compare this to what we did with continuous time systems, where, in one sense, what we were doing was letting this interval that you're taking changes over shrink down to 0, right? It's in the same way that we define the derivative by letting the time interval go to 0, t plus h and t, for example. Well, in this case, we're keeping these things discrete. You have a discrete change. That's what my delta represents. In order to move from one time to the next. Now, typically we write this in vector notation. We don't like to have to keep writing all of these equations. We like to write it as just delta x is equal to, let's call it capital F of x. F would be your vector of all of your functions, f1, f2, f3, all the way to fn. Delta x, that is just the change of each one of these things. And what this really represents is your value at your next time step minus your current time step. So in this case, your units of time are scaled to be natural numbers. So that's my n here, right? The current instance, or the nth instance of time, and then the next instance of time. Okay, so you could be walking by seconds, by days, by weeks, whatever it happens to be. All you're saying here is you're letting these things be indexed by the natural numbers. Now, one thing that you can see about this formulation right here is that it can be arranged to tell you, if you know what's happening now, you can find out what will happen next. Because if you have this change, delta x, if you use this, this tells me, okay, what's happening next is going to be what is happening right now plus the change. Right? So if you look at this on the right-hand side, everything is a function of what is currently taking place. This is just like Newton iteration, right? So Newton iteration, we saw that we have our current value and then an update. That's the same thing that's happening here, and it tells us where we are going next. So in fact, you could always think of Newton iteration as an example of a discrete dynamical system. Now, on top of this, you need an initial condition, just like differential equations. So initial conditions come in exactly the same form as they would for differential equations, and that means that you need to know what happens at the start. You need to say at 0, n equal to 0, so when you start counting time, how does the system become initialized? So again, if this is representing, for example, your Newton method, this is your guess at your root, and then you might be updating it according to some discrete dynamical system. Now, let's talk about something that we have seen already pretty extensively when it comes to differential equations, and that is steady states. Steady states. Now, we saw with continuous time differential equations that steady states represent values of the state variables x for which there is no change taking place in the system. Now, in this case, for discrete dynamical systems, it's actually a little easier to understand what steady states would be, because all along the left-hand side of our equation here is the change in the system. So if there is no change in your system, that tells you that this delta x is equal to 0, right? Delta x1 is 0, delta x2 is 0, all the way down to delta xn is 0. That means from one time step to the next, nothing is changing, right? Whatever I'm observing today will be the same as tomorrow, will be the same as the next day, and so on and so forth. And that means that you are solving for roots of this function f that describes the change, right? So taking this equal to 0 sets this whole side equal to 0, which gives me, whenever I isolate for the right-hand side, this thing. So one thing that you might think about is if you have seen a discrete dynamical system before, you typically see it written in this form, right? The next state is a function of the current state. The reason I'm writing it in this form is because it is a little bit easier for you to think about steady states, at least in my opinion, right? It is much easier to think about changing from one state to the next than it might be from updating one state to the next. So we're going to sort of go back and forth between these two ways of looking at things. But what I want you to notice is that steady states make a lot more sense when you have it in this formulation. Okay, now the last thing that we can think about is what's called stability. So we would say, let's say let x naught in S be a steady state. Okay, so let's imagine we have a steady state. This means that f of x naught is equal to 0, right? I found a root of my update or my change function f. Then I would say that, so then x0 is stable if for all initial conditions close to x0, so close to x0, xn, the sequence generated by these updates, converges to x naught, okay? So I'm purposely being a little bit vague here, right? I'm saying close, I'm not telling you how close. Unfortunately, that's system dependent, right? If you spent a lot of time with Newton iteration and you did it on a bunch of different examples, you probably saw that things vary from function to function that you're trying to find the roots of, right? It depends on how complicated that function is. That will tell you, how good of an initial guess you have to have, okay? Now, all that the stability criterion is really saying is that there is a potential, right? As long as you start close enough, as long as your guess is good enough, you're going to get there. That's how you should think about this, okay? So it's not telling you how close you need to be, but it says that there is a possibility. If you are close enough, you're going to fall into that. And again, always think about this in the context of Newton iteration, right? At least initially, because that might be the best way to really intuit what's going on here. Now, beyond something like Newton iteration, there are examples that you probably are familiar with when it comes to discrete dynamical systems. Anything that really has a discrete update rule can be formulated as a discrete dynamical system. Now, one that you probably know is the Fibonacci numbers. Let's let f of n equal to the nth Fibonacci number. Pardon me. Fibonacci number. Okay, then what you know about the Fibonacci numbers are that you can take the previous two, f of n and f of n minus 1, you can add them together to get the next Fibonacci number. And we also know that f of 0 is 0 and f of 1 is 1, right? You've done this probably before, right? So the first two elements of the Fibonacci numbers are 0 and 1. You add those together, you get the next element. That's going to give you 1 again when you add these two things together. Then you take the previous two and add them together, so 1 plus 1, that gives you 2. Then you take the previous two and add them together, you get 2 plus 1, that gives you 3 and 5 and 8 and so on and so forth. So in some sense, this is already a discrete dynamical system. It has an update rule, just like Newton's method. What I'd like to do is I'd like to write it in the form that I have right here. So how can I reformulate this thing to make it into my maybe more familiar form or make it conform to what I have already on the board? Well, here's what I could do. I could set x1 of n, right? So the first variable equal to the previous Fibonacci number. And I could set x2 of n equal to the current Fibonacci number, okay? So what does this actually mean for me? Well, it tells me that the next x1 of n, that is going to be, so if I put n plus 1 in here, I get f of n, which is just x2, right? I want to write everything in terms of x2 and x1, right? I want to do away with the f's here. I want to write it in this nice system form that I have. Similarly, if I did the next x2 value, that would put an n plus 1 in here. That would put an n plus 1 in here. But using the Fibonacci recurrence relation, I've got, this would be x2 of n plus x1 of n, right? There's x1 right there. There's x2 right there. So I have a new way of writing the Fibonacci sequence in terms of this discrete dynamical system that sort of conforms to my setup that I had over here. Now, the other thing that we could do is we could actually write it in terms of this delta notation as well, right? So all you need to do is subtract x1 from both sides here. So in this case, you would get delta x1, let's say, of n. So this is x1 of n plus 1 minus x1 of n. This would be x2 of n minus x1 of n, right? The way that I got the delta here is I subtracted x1 of n from both sides of the equal sign to preserve the equality. Similarly, I can subtract x2 from both sides of this piece right here, and now I get x1. So that tells me the change in x1 comes from the difference between x2 and x1 at your current step. The change in x2 is just equal to whatever your value of x1 was. The other piece of this is your initial conditions, right? So you can actually use these initial conditions right here. And let's see how they feed in. I actually get that x1 of 0 is equal to 0 and x2 of 0 is equal to 1. But if you wanted to make up your own Fibonacci sequence, you could just start with any values that aren't 0 and 1, right? Maybe you wanted to start with 5 and 10 or -2 and 3, right? Those are perfectly valid. Those are just different initial conditions that completely fit into this framework. The only thing that you need to do is potentially use this update rule or use this change rule, and that will generate out a sequence for you according to the same rules that Fibonacci abides by. Okay, so according to my calculations, now you've got at least 2 discrete dynamical systems that you can sort of get your head around and you can sort of chew on a little bit. You've got Newton updates, or Newton's method, in both one dimension and in multiple dimensions, right? They're both examples of discrete dynamical systems. And the Fibonacci numbers. Let's do another example that's going to become useful as we progress through the rest of this lecture series. So let's take a look at a very, very simple version of this. And I want you to really see what's going on here. So let's consider a 2-dimensional system, x1 and x2, and consider, so a very, very simple system. The change in x, again, written as vector notation to abide by what I have right here, is equal to minus lambda of x, okay? And in this case, lambda is a positive number. So it says if you want to change x, well, the way you're going to change it is by changing it appropriately according to negative lambda times your current state. So the question is, what happens, right? How can we analyze this system? Well, the first thing we can see is that the steady state here, well, in our case, we have f of x is equal to minus lambda x. That's the right-hand side, right? Abiding by this notation right here. And f of x is equal to 0. Well, that's only going to happen if x is equal to 0. All right, so if you're at the origin in the 2-dimensional plane, when x1 and x2 are both equal to 0. So we can ask ourselves, is this stable, right? Is it possible that if we start this iteration scheme, this update, close to 0, are we going to fall into 0, or is something weird going to happen? Well, let's write this. So let's expand out our change and write it as an update, okay? So now our system becomes x1 of n plus 1 is equal to, so I take the x1 onto the other side, and I get 1 minus lambda times x1 of n. Similarly, x2 of n plus 1 is equal to 1 minus lambda x2 of n. Right, so you can see that they've completely decoupled. If I want to understand one, I can just, if I want to understand both, I can just analyze one at a time. I can tell you what will happen for both of them if I just understand one of them. Okay, so let's look at this. If I have an initial condition, then x1 of 1, my next iterate, right? So n is equal to 0. That gives me my initial condition. The next piece is taking n equal to 0 here. This is just 1 minus lambda times what I started with. Similarly, if I want to do this to get x2, the second iterate of x1, pardon me. Well, this would be taking n equal to 1 in here. N equal to 1 gives me x1, which I know can be written in terms of x1 of 0. So in this case, I get 1 minus lambda squared, 1 coming from this x1 of 1, and 1 coming from the original recurrence relation, and then times x1 of 0. And it doesn't take too much thinking to recognize that in general, all you are going to do is keep adding or keep multiplying in a power of this 1 minus lambda every time you take an iteration. So we can ask ourselves, what happens, what is the limit as n goes to infinity? because that's exactly what we wanted to look at right here, right? So this was, again, this was a limit as n goes to infinity in this case. So the sequence that's generated by doing this iteration scheme, does it fall into 0 or not? Well, first of all, we know that the limit as n goes to infinity of 1 minus lambda to the n, well, in our case, this thing is going to be 0 if and only if minus 1 is less than 1 minus lambda, which is less than 1, which is the same as saying 0 is less than lambda, which is less than 2. Okay, so basically you have to be exponentiating something that's between minus 1 and 1. That's this condition right here. And whenever I swap things around and isolate for lambda in the middle, that's the same as saying lambda is between 0 and 2. So let's take a look at what this says. This says that if lambda is between 0 and 2, then any initial condition, no matter what it is, it doesn't even have to start close to the origin. Any initial condition leads to a sequence that when you start taking successive iterates in this system, this 1 minus lambda the n is converging to 0. It's getting very, very small. And since this solution is the same, so similarly you have x2 of n is 1 minus lambda to the n, x2 of 0. Both of these things are going to converge to 0. So this tells me that x equal to 0 is stable. Right? It doesn't matter where you start, you are always going to go into 0 when lambda is between 0 and 2. Now you can turn that on its head as well, right? You could say, what if lambda is bigger than 2, right? So I made the assumption that lambda is bigger than 0. So what happens if I go outside of that region? Well, if lambda is bigger than 2, 1 minus lambda is a number which is an absolute value larger than 1, which when we take numbers that are bigger than 1 and we take exponentials of them, they blow up, right? So for example, if you take minus 2 to some power, it's going to be minus 2, 4, minus 8, 16, minus 32, 64, right? So that's blowing way, way, way up. So in this case, x equal to 0 would not be stable because nobody is going to settle into x equal to 0 no matter how close you start. You could pick x1 and x2 extremely small. Think about the smallest number you could ever think of. You could start x1 and x2 there. As long as it's not 0, you could start at that, and eventually, if lambda is bigger than 2, these things are going to blow up. You're always getting pushed away from x equal to 0. So then you can actually think about, what happens at some of the edge cases. Well, at lambda equal to 2, this gives me that x1 of n is equal to minus 1 to the n, x1 of 0. And x2 of n is equal to minus 1 to the n, x2 of 0. In this case, you never do anything. All you do is flip back and forth between plus and minus numbers. You don't get closer. You don't get further away. All you do is flip back and forth. Nothing exciting. So in this case, you don't really have stability, right? Because you never actually converge into your equilibrium point. But you also don't have sort of instability, right? You're never getting pushed away from it either. So this is one of those sort of weird intermediary spots where all you do is just kind of flip back and forth. Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, and so on and so forth. Now the other thing I want you to notice is that if lambda is between 0 and 1, then 1 minus lambda is positive. Now, why is that interesting? Well, that means that each successive iterate is multiplying a positive number. So you never change the sign of your initial condition. If you started with a positive value, you always get a positive value and converge into 0. If you started with a negative value, you stayed negative and you converge into 0 up from the left. But if you are between 1 and 2, this would give you that 1 minus lambda is less than 0. So now you're still converging to 0. You're still in the stable regime, right? You're still in my stable regime, but you're flipping back and forth, right? Whatever x1 was, then you go to a smaller value, an absolute value, but negative. You flip to the other side of 0. Then you flip to the other side, you flip to the other side, and you are slowly sort of tinkering and falling into 0, but you're doing it by hopping back and forth over that equilibrium point. And of course, the last case that I left down here is if lambda is equal to 1. If lambda is equal to 1, I mean, nothing really that interesting happens because this is 0, and so you fall into the equilibrium in one step. Right? Whatever your initial condition was, your next point is 0. You're gone. Okay, so this was a little bit of a rough, quick introduction to discrete time dynamical systems. Over the next few lectures, we're going to get our hands a little dirtier with these things. And then, once we feel a little bit more comfortable analyzing and interpreting discrete time dynamical systems, maybe through graphical methods, through some sort of rougher methods, then we're going to zoom out a little bit and look at dynamical systems as a whole and look at some of the analytical methods that we have. These pencil and paper ways of trying to determine things like what are the equilibrium points, what is the stability of these equilibrium points, how do solutions behave. But first, we're going to get some intuition. We're going to do a lot of graphical stuff. So I'll see you in the next lecture.